Welcome to class, everyone. We will get back to this problem in a few slides. So the reason why I put that problem at the start of class and why we'll be discussing it is because it's some additional context that I thought might be useful for people in problem 3 and just providing a bit of intuition for why that's an interesting problem. So we'll see that later in class. The office hours for Vincent are now at 11 a.m. Thursday, this week only. And for me, they're again at the normal time of 10 a.m. on Friday. This is a baby fennec fox, which is a fox found in the desert of, I think the Sahara. Are there questions? We didn't finish with dynamic programming. The first thing we're going to be discussing today is dynamic programming. And then we'll just circle around to problem 3 and just a little bit of context for MaxFlow in that context. If we have time, we can also look at MaxFlow as a linear program, but I think we probably won't have time for that. Okay. So as a review from last time, dynamic programming is a paradigm of algorithm design in which the solutions to smaller subproblems are calculated and reused. So one way of doing this, as we discussed, is to solve all the possible subproblems. In order of increasing size is often the way that one does that, so that one has all the solutions that one needs. So the smallest subproblems will get reused in the slightly larger subproblems, and then those ones will get used to make slightly bigger solutions, and so on, until you get whatever solution you want. So ordering them is really important in that case. Alternatively, you don't have to necessarily compute them all beforehand. You could just compute them as they're needed. That's sometimes useful if you don't know exactly what subproblems you'll be needing. And this is called memoization. Again, memoize, to make a memo out of something, to just store the solutions to the subproblems. In case you're wondering about the name dynamic programming, so this was chosen by someone called Richard Bellman, and they chose this word because it sounded awesome, basically. And Bellman thought that it was impossible to use this word in a pejorative context, so in a context that was making it sound bad. It also has a very interesting property, said Bellman, as an adjective, and that is it's impossible to use the word dynamic in a pejorative sense. Thus, I thought dynamic programming was a good name. It was something not even a congressman could object to. Apparently also Bellman was influenced by trying to sound like linear programming and trying to make it even more awesome sounding than linear programming. Okay. So let's see another context in which dynamic programming can show up. How fast is a naive algorithm to multiply matrices of size m by n and n by p? And by naive, I mean just like the basic thing that you would do, nothing really fancy here. There are a few different suggestions. So the result is a matrix of size m by p, definitely. And each entry of that matrix is going to be a sum of n different, I said entries, but I guess I should have said a sum of n terms, because in order to calculate each of those entries, you're basically computing the dot product of two size n vectors, a column and a row. So given that each of these MP entries is the sum of n different things, the naive time is just m times n times p operations. Or really, it's theta of that. So it's theta of m n p operations. I'm gonna write it as m n p. In the particular case that all the matrices are square in size n by n, then you get time n cubed. Now, there are ways to speed that up for square matrices. But the naive algorithm, certainly for general matrices, we have m times n times p. Questions? So suppose we multiply matrices of size 10 by 100, 100 by 5, and 5 by 50. How long will that take? Depends on the order. So let's see. If we multiply A times B first, and then multiply by C, the time to multiply AB is 10 times 100 times 5, since those are the dimensions of A and B, and that's 5,000. And then we have to do the second multiplication, where the dimensions are the dimensions of AB, which is 10 by 5, and 5 by 50 for C. So the second multiplication is 10 times 5 times 50, 2,500. Overall, we have 7,500 operations. What if we were to do the other order, A times BC? Is it the same? So let's see. If we multiply A by BC, to calculate BC, we have a 10 by 50 matrix, which will take 100 by 50 matrix. We have 100 times 5 times 50. So that by itself is 25,000 operations, just to multiply B times C. And then to multiply BC times A, we have a 50 by 100 matrix, which 100 by 50 matrix BC. We're multiplying that by A, which is 10 by 100. So we have 10 times 100 times 50, 50,000 for the first multiplication. So the total is 25,000 plus 50,000, so 75,000. It's 10 times as much, just by changing the order in which we do the multiplication. if you're surprised by why it can change so much. I mean, think about the fact that here we basically got rid of the 100 by multiplying it as an inner dimension within a 10 by 100 and a 100 by 5 matrix. So we ended up with a 10 by 5 matrix, which was super small, and then multiplying that by a 5 by 50 matrix was really easy. But then if we did it the other way around, we're doing 2 multiplications by matrices with 100 as one of their dimensions. So those are going to take a really long time. Questions? Okay, so suppose we're given matrices in general, like a bunch of matrices, and they all chain together. So the dimensions of the matrices are nice. They're compatible with multiplying them in order: P1 times P2, P2 times P3, P2 times P4, and so on. What's an efficient algorithm for working out the most efficient order in which to multiply the matrices? Somebody's guessing that it's dynamic programming because we're talking about dynamic programming. So there's a question. Can you clarify what is meant by operations in any arithmetic operation? It's a really good question. So going back here, the number of, by operations, I mean just like multiplying or adding basic things. Each of these operations is sort of, you can imagine it being constant time if all of the entries are like float 32 or something. That it just is, it takes a certain amount of time to multiply 2 float 32s. Question, is this rod cutting? Rod cutting was what we did last time. This is not rod cutting, this is different. Can we try greedy algorithms? Not clear to me how you would make it work with greedy algorithms. Basically, one of the reasons why a greedy algorithm might be a bad idea here is that a decision you make, you might paint yourself into a corner by deciding to multiply 2 matrices that then turn out not to be the right ones. But you could go and try to find a greedy algorithm. Choose matrix multiplications that don't result in larger matrix results. So you can come up with a bunch of different heuristics for it. And maybe you could come up with a set of rules that would work very well. I don't think that there's a way to do that. So let's just, first of all, think about trying all the possible ways to do it. So for example, if we had 4 matrices, these are ways that we could imagine multiplying them. I'm using parentheses here to sort of indicate the order in which we're multiplying things. So this is multiplying A3 and A4 first, then multiplying that by A2, then multiplying that by A1. And here you have A1 times A2 and A3 times A4, and then you multiply both of those together. There are 5 different ways to parenthesize these. So let Pn be the number of ways to parenthesize the product of n matrices. What's Pn? Like, how big is Pn? Can we just try all the possible ways? I mean, this is just 5 ways. Doesn't seem too bad. We try to work it out as a recurrence. Let's try to work it as a recurrence. Let's think about a recurrence relation for Pn. We could imagine thinking about the last product that we're doing. So the last product is, we had multiplied the product of some k matrices, and then we're multiplying that by the product of the remaining n minus k matrices. So for example, here we're multiplying 2 matrices, and then we're multiplying the other 2 matrices, and that's what we're multiplying together. Here we're multiplying 1 matrix by just a single matrix, and then we're multiplying it by 3 matrices. So the last time we're doing a multiplication is by some k, and then the remaining n minus k. And so we can write a recurrence where it's just the number of ways to multiply the first k here, and then the number of ways to multiply the remaining n minus k. So the total number is going to be just the sum of pk times pn minus k as k varies, because we don't know what the last multiplication is. The last multiplication might have been multiplying the first 10 in some order, and then the last 15, or it could have been the first 15 and the last 10, or it could have been all but one of them and then just multiplying by that last one. So yeah, this will give us all the possible ways to multiply. Questions? How big is this roughly? How big is Pn? Is it linear, cubic, exponential? Silence. What do people think? Can we also use regular expressions to prove this? Like proving the number of different ways to parenthesize something. Yeah, that's a really cool connection. Maybe talk about that later. I'm not sure exactly how one would use it to count, but yeah, I mean, that's totally a connection that one could make here. Do you also have to make sure? Yeah. No, it's really interesting. So there seems to be general consensus that it's exponential. Indeed, it is exponential. So it turns out the solution is the Catalan numbers, which grow exponentially. And so I'm just going to do a little bit of a side note to the Catalan numbers because they're really awesome. So mentioned them before in the context of binary trees. So let's just look at what the Catalan numbers are. If you like the Fibonacci sequence, and you like just like sequences of numbers, the Catalan numbers are in many cases, like some mathematicians would argue they're more interesting than the Fibonacci numbers. They turn up more places maybe. Yeah. So the Catalan numbers are this sequence of numbers 1, 1, 2, 5, 14, 42, 132. And if you're not immediately seeing the pattern, that's fine. There is a pattern, but it's not super simple. And they grow exponentially. And they're normally denoted C0, C1, C2. They satisfy this recurrence relation. This is not exactly the same as what we saw before. And that's because we were looking at Pn equals Cn minus 1. We were shifting them over. So we normally denote C0 as the first Catalan number 1, but we were looking at P1 as being this Catalan number, P1, P2, P3. But you can, so Cn minus 1 is just the number of ways to parenthesize n matrices, or n elements. You're multiplying together. And there's another connection to the number of binary trees. So the reason why it's also the number of binary trees is binary trees and parenthesizations. They just turn out to be the same thing. You can think of a binary tree as being an order in which you multiply the leaves together, basically. Like the binary tree, like if you have two children, then you say, okay, I'm multiplying those together, and it's teaching you the order in which you multiply everything. So that's connection between numbers of binary trees and a number of ways to multiply things, parenthesize things. There are lots of other interpretations of the Catalan numbers. Here's another cool one. Number of ways to triangulate a convex polygon with n+2 sides. So for example, this is a regular hexagon, so n equals 4. So we should have the fourth Catalan number, 0, 1, 2, 3, 4. It's 14 ways. Here are the 14 ways to triangulate a hexagon. And so you can, triangulation is just like cutting it with lines between some of the vertices so that you end up with triangles. So you could end up with these. You're always going to have the same number of triangles. You're always going to have 4 triangles if you're cutting up if you're triangulating a hexagon. And there are many different ways for those triangles to arrange themselves. And then there is and then yes, so I particularly like these ones. They're very pretty, but yeah, sorry, there was a comment. I'm just looking at the comment. Yeah, so the reasoning why there is the number of ways to triangulate a convex polygon is the same as the Catalan numbers, is because you can, again, imagine looking at this recurrence relation where you say, okay, well, I'm going to look at a diagonal from this particular vertex. Well, it could go to any of these other ones. So I'm going to look at k equals 0, k equals 1, k equals 2, k equals 3, all the way up to n, basically. And once I've taken that diagonal, I can dissect it into a problem over here, how to dissect this polygon and how to dissect this polygon. So that's why you end up with this recurrence relation coming out of the triangulations of convex polygons. If you didn't get that, don't worry. But yeah, there are so many different ways to come up with the Catalan numbers. They turn up all over math. And they actually have a closed form expression, which is this. The number of ways to do all these things, it can be written just in terms of this nice binomial coefficient. 1 over n plus 1 times 2n choose n. Are there questions? And yes, this is exponential in n. I'll let you think about why that's the case. Question. Okay, let's move on. So anyway, point being, you don't want to go through exhaustively all the possible ways to multiply together all the matrices. Let's do it in a more efficient way. How can we use a dynamic programming approach? So yeah, we can basically, we were sort of dividing the multiplication into two pieces. We can imagine doing that a bit. So we know that we can split a product into the first k matrices being multiplied together, and then the last n minus k matrices are also being multiplied together for some k. And the critical thing here is, this is the important thing in dynamic programming, is that if you take a subproblem, the solution, the subset of the full solution is a solution to the subproblem. So if you take an optimal parenthesization of the whole thing, and you take a look at just if you take a look at if you break it into the last multiplication, which is some k and then the remaining n minus k, if that's the last multiplication you're doing, then each of those has to be an optimal solution for the first k respectively and the last n minus k respectively. So for example, if we knew that the optimal way to multiply a1 through a10 was to first multiply a1 through a6 in some order, and then multiply that result by a7 through a10, again, multiplied in some order. We don't know what the order is. If we knew that the optimal way to do it, then we could just say, OK, we can find the optimal way to multiply these, and then combine it with the optimal way to multiply these. Because a subset of an optimal order is going to be an optimal order. That's the important thing in dynamic programming. We'll see an example in a bit where this isn't the case, or sort of seems like it might be the case. In this case, yeah. So we can use these smaller subproblem solutions to get our bigger solution. So suppose the optimal parenthesization of a1 through ak takes this number of operations. So what is this? Well, we can just say the number of ways to do it, if we broke it at k, the first k and then the last n minus k, would be this number of operations is the optimum for the first k. This number of operations is the optimum for the second block of n minus k. And then we have to actually multiply these two together. And so that's going to be P1 times the inner dimension, which is pk plus 1. Remember, these are the dimensions of the matrices up here, times the outer dimension. And we just, this depends on k, where we broke it. And we just take the minimum over all k. Questions? It's just saying, we decide, OK, we're first going to multiply the first k. We're separately going to multiply the last n minus k. And then we're going to take those two products and we're going to multiply them together. We're going to have to do that for some k. We don't know which k it is, so we have to take the minimum over all of those. And importantly, we can compute the solutions to these things first. Just do this sort of dynamic programming thing. Questions, things that aren't clear. OK. So we're only going to need the products of consecutive matrices. So let's go back here and let's look at which things we're going to have to store. I'm going to type some things in the chat. Are we going to have to compute the product A1, A2, A3? Like sorry, I guess I should have said, are we going to have to compute f of A1, A2, A3? Will that be one that we have to compute? I'm writing things in the chat. Yes, we're going to need that one because that will be what happens when we take k equals 3. We're going to have to compute a function of a1, a2, a3. What about function of an minus 1, an? Will you have to compute that one? Yes, we will need to compute that one when k equals n minus 2. It's a very easy one to compute, function of an minus 1, an, because it's just there's only one possible way to multiply two matrices. But yes, we will need it. Here's a trickier one. What about, there's a question. So what we're doing is we will say, okay, what if if we're going to compute function of a1 through an, and by the way, really well done for saying if you're confused. It's way easier for me to tell when I'm like looking at a classroom of people and people can like, it's obvious, but if I'm not looking at you, it's really necessary for you to tell me. So thank you. We're computing the minimal number of operations to multiply all n together, and we're saying, okay, there are many ways that we could have decided to multiply the first k and then the last n minus k separately, and then bring those together. That could be our last multiplication. So for example, we could have a1, a2, a3 multiplied together, and then a4, a5 separately multiplied together. And then we'd have to recursively work out what's the best way to multiply a1, a2, a3, and what's the best way to multiply a4, a5. So we're saying, okay, there are many possible ways to split it. So we could have done with k equals 1, which would be a1 times a2, a3, a4, a5. Or we could have done k equals 2, which would be a1, a2, a3, a4, a5. Or we could have done it in other ways. So we can split it at any k, and we're going to have to recursively work out what is the best way to multiply these by themselves and the best way to these by themselves. And in order to get if we were to split it that way, if we were to split it, say a1 through a6 and then a7 through a10, we would have the total number of operations being function of a1 through a6, function of a7 through a10, and p1 times whatever it is, p7 times p11, which are the dimensions of those matrices. So if we're multiplying this by this, then it would just be the first dimension of this matrix times the second dimension of this matrix times the last dimension of this matrix. What if we picked k, the k we picked wasn't the best in the beginning? Yeah, that's why we're taking the minimum. It's just the minimum over all the possible ways to do this. We definitely don't want to just pick any k and guess. We want to try all the possible ways to split it. Assume we've already worked out the best way to decompose. How is this more efficient then? Ah, yes, good question. So the reason is because we'll compute these super efficiently. We're going to pre-compute the solutions to these subproblems. So let's again go back. If we're trying to compute these products, which of these are we going to need? We're definitely going to need f of a1, a2, a3, because that is k equals 3. We're going to need something like a n minus 2, a n minus 1, a n for k equals n minus 3, etc. But then what else do we need? Will we need something like f a2, a3? Will we need to compute that? Or will we need to compute f of a3, a4, a5? Suppose we are trying to, so in the process of working out f of a1 through an, will we ever need to work out f of a3, a4, a5? Will we ever need that? So yes, we will need it, because if we're trying to compute f of a1 through a5, we're going to recursively do this process. So we're going to need f of a3 for a5 in order to compute f of a1 through a5, which is needed to compute f of a1 through an. So do we have to just try all the possible matrices? Will we ever have to, will we just try to have all of the possible sets of matrices? Well, no. What we're going to need is we're going to need the products of consecutive matrices. So suppose for each I and j, and if you got confused by the previous stuff, this is a good time to dial back in, because what the previous stuff was intuition for why this is our algorithm. So suppose for each I and j, we've pre-computed function of ai through aj. And again, that is the minimal number of operations needed to multiply these matrices. Suppose that for every I and j, we've pre-computed this. So let's use induction on how many matrices. Suppose that we can do this for any ij with j minus i less than or equal to m, and now show that we can do it for j minus i equal to m plus 1. So like we previously could do it for up to m matrices, and now we can do it for m plus 1. How are we gonna? Let's see that we can do this. But first of all, what is a good base case? Yes, we're inducting on n. Two matrices is a perfectly fine base case, but let's actually make it be only one matrix. So j minus I equals 0. The number of operations we need is just 0. We don't have to multiply anything. Always pick your base case to be stupidly small. OK. Now suppose that for j minus I is less than m, we can do this. We can we have the optimal number of operations for multiplying anywhere up to m consecutive matrices from our list. So if m is 3, then we can multiply, we know how the optimum for any 3 consecutive matrices in our list. Now let's prove it for m plus 1 consecutive matrices. Well, we know that just the same recursion, recurrence relation that we had before, the minimal number for this whole block is if we split the block somewhere, multiply those first, multiply the remaining ones, and then multiply all of the, and then take the first block and the second block and multiply them together. And then here is the cool part. We've already computed these because that's fewer matrices. We already knew that we could do it for anywhere up to m plus 1 matrices. So we already have computed this, and we've already computed this. So the only thing that we have to do is take the min over all of these things. And how many things are there? Well, they're j minus I things, because they're j minus I choices of k, j minus I choices of where to split it. So the overall time is theta of j minus I, because we pre-computed these. So that finishes the induction. We know how to do it. But let's work out how long it takes us. Because we're going to have to do this for every I in j, working upwards from m equals 0 to m equals n. What is the total time if we want to do this for I equals 1 and j equals n? We're going to have to do this for all the other, for all the smaller i's and j's, for all the smaller m's. What's the total time, again, for, what we want is f of a1 all the way up to an. How long will that take? Any guesses? Just guesses. Fine. Again, the question is, what is the overall time it takes to compute f of a1 through an? So if we're multiplying n matrices. OK. So it is actually a little bit higher. It's going to be n cubed. And here's the reason. So you're going to have to do this for every possible ij, for every I between 1 and n, and for every j between I and n, so every j greater than I. And for each of those, it's going to take time theta of j minus I. And you do it in order by m. So you start out with j minus I equals 0, and then you go to j minus I equals 1, and then you go to j minus I equals 2. And you deal with all of the one, basically what you're doing, all this j minus I, just it's a formal way to say, let's pre-compute all the optimal way to multiply any 2 consecutive matrices, then every 3 consecutive matrices, then every 4 consecutive matrices. Once we've done all the things up to 4, we can do the blocks of 5. Then once we've done all the blocks of 5, we can do the blocks of 6. Once we've done the blocks of 6, we can do the blocks of 7, and so on. And so in order to do all of the blocks of matrices, we're going to have to sum theta of j minus I over all possible j and I. Let's just rewrite that. I'm just shifting j by I. So now this is theta of j as j goes from 0 to n minus I. And this is just the sum of 1 up through n minus I. So it's theta of n minus I squared. But then you still have a sum over I. And so it becomes a theta of n cubed. And if you want an intuition for why the sum of squares is cube of n, the sum of 1 squared, 2 squared, all the way up to n squared is n times n plus 1 times 2n plus 1 over 6. We proved that in the, or we looked at that in the induction class. I will come back to this at the end for any additional questions, but I wanted to cover a couple more things. So I will come back to this right at the end for, however long people want to stick around and discuss this. Let's take a look at a way easier application of dynamic programming. Shortest paths. We were essentially doing dynamic programming when we were looking at Dijkstra's algorithm. We were essentially breaking it up into the smaller problem and computing the shortest paths from from your starting vertex to every one of the closest vertices. You started out doing the shortest distance, the one that was closest. Then we did it the one that was next closest, and then we did the one that was next closest, and so on. And this was basically dynamic programming, where we were using the solutions to the previous problems, the distances to the closer vertices, in order to prove a distance to the next one. Basically dynamic programming here. And the key property that we used is if we had a shortest path between two vertices, then we can break that, if we break that shortest path at any point, the first part of the shortest path is a shortest path itself, and the second part is also a shortest path. Again, the key point here in the dynamic programming is a subset of a shortest path is a shortest path. For example, if I know that the shortest path from S to X is this thing, then I know that the first part of it is a shortest path from S to T. Because if there were a shorter way to get from S to T, then I could take that and shorten the overall path to get to X. So that means that if I pre-compute the shortest path from S to T, I can use that to get the shortest path from S to X. So that was the reasoning behind Dijkstra's algorithm, and it's basically just dynamic programming. Here is a quick intuition for why that doesn't always work. Suppose we were trying to find longest paths. Can we use a similar dynamic programming approach to find the longest path between U and V without any repeated vertices? The answer is no, and here's the reason why. If we're trying to find the longest path between, say, Q and T, QRT is a longest path from Q to T. It's the longest way to get from Q to T without repeating vertices. But if we break it into two smaller subproblems, QR and RT, those are not actually longest paths. The longest path from Q to R is QSTR, and the longest path from R to T is, for example, RQST. The critical point here is that dynamic programming only works if you can break something into smaller problems, where the solution to the big problem is built off of solutions to small problems. In the case of shortest path, a big shortest path is made up of two smaller shortest paths. In the case of longest path, a longest path is not necessarily made up of two longest paths. Let's end with the intuition for problem 3 on the problem set. Let me just respond to a quick question, and then we'll get this context for problem 3. So for longest path, are we still assuming there are no negative edges, or it doesn't matter? I mean, it's not going to work either. Even if either way, we can just assume that if it's all positive weighted edges, yeah. Okay. So This is important for thinking about problem 3. Augmenting paths is just as a quick review. Given a flow network and a flow in it, the residual network is defined by saying, okay, this is the flow, again, the flow along all the edges of this network. Here it's 11 out of a possible 16. The capacity is 16. The flow is 11. Here the capacity is 20, and the flow is 15. The residual network is made from the original network by saying you can go back. You can backtrack by the amount of the flow. So here, the amount of the flow was 15. So you can backtrack by 15, or you have 5 more that you could take in this direction. So there are edges going both ways, both in the original direction, because there's 5 left, and in the backwards direction, because there's 15 that you can take back from the flow. So given the residual network, an augmenting path is a path in the residual network from the source to the sink. So for example, this is an augmenting path. And the basic idea of the augmenting path is that you can augment your original flow by flow along this path. So given this original flow, you can construct this residual network. You can find this augmenting path in the residual network. And this augmenting path, the minimum capacity along all of its edges is 4. So we can add 4 to every one of the edges in this original flow. So we could now, instead of having 8 here, we could have 12, 8 plus 4. Here, we originally had 4 going in this direction. We can backtrack by 4 and make this be 0. And here we have 15 before, and now we add 4 to it, and it becomes 19. So overall, the net flow in the network increased by the amount of the augmenting path. So adding an augmenting path to a flow is just adding the flow along the augmenting path. And the flow along the augmenting path is the minimum capacity along any of its edges. Now, Ford-Fulkerson works by iteratively finding augmenting paths in the residual network, adding the new path to the flow, recomputing the residual network, and so on. So here's an example of a flow network where we could pick an augmenting path of capacity 1 million along the top, and then we could pick another augmenting path of capacity 1 million along the bottom. That would finish the algorithm in 2 steps. That is not the only way to do it, though. We could pick bad augmenting paths. We could pick an augmenting path like this. If we did this augmenting path, this would be our residual network. The residual network, if this augmenting path has minimum capacity 1, so we would have to only send flow of 1 along here. What's our residual network? Well, our residual network is similar to the previous one. We can go back now by 1 here. We can go back here by 1, back here by 1. There's 999,999 left that we can do in this direction, and similarly here. And then these 2 edges, we didn't have any flow, so they're the same. We can find another augmenting path now in this residual network, and this augmenting path could be this. If we use this augmenting path followed by this augmenting path, we end up with this residual graph. Each one of these augmenting paths just used flow 1. And you can see that we can keep on doing this. We can have another augmenting path like this, and another augmenting path like this, and we can keep on basically reversing the direction of this edge. And each augmenting path backtracks along this edge, and so we only add flow 1 each time. So we could end up having 2 million augmenting paths if we did it in this order. The idea here is that the particular augmenting paths that we choose really dictate how long Ford-Fulkerson takes. This is an example where we could choose 2 really good augmenting paths, but we could also choose augmenting paths in such a way that we end up having to choose 2 million of them before the algorithm ends. The algorithm is going to end either way, but there's a lot of difference in how long it takes. If we had hindsight, maybe we could pick fewer augmenting paths. So that's the intuition for problem 3. Now I'm happy to answer any questions about this or any of the previous things. I realize there was a lot that we covered today. I'm happy to stick around a bit longer, or feel free to shoot me questions in the Slack.